All right. For those though maybe don't know, the first part is what is a BMC? I assume most people know, but it's a base management controller. It's what mostly from our perspective goes inside our servers. It provides a variety of function, most out of band type stuff. So you haven't powered on your server, the OS isn't running. You can use your BMC to power the system on, to monitor for stuff. BMCs usually support a variety of protocols. For the longest time, IPMI was really the standard. That's just your very normal standard IPMI protocol for managing servers. From an OpenBMC perspective, we've also got a REST API, and there's also an up-and-coming standard that's kind of replacing IPMI, which is Redfish, and OpenBMC also has a bit of that. The BMC provides a lot of data collection, so what power sensors, thermal sensors, different aspects of your server. Debug, if it crashes, it provides error logs and other types of information. It's usually got a GUI of some sort, so you can bring up a web browser to it and manage your server. OpenBMC, has that as well. It can be an interface over to the host, providing things like virtual media, where you want to install OSs and such. From an OpenBMC perspective, ours is based on OpenEmbedded, which is a technology an open source technology that lets you basically build custom Linux distributions. And that's basically called Yocto. And then, Yocto is its own thing out there that OpenBMC is based on. And we use the normal Linux kernel. Joel will be talking about that later, I think. We're even basically on the latest and greatest, right? Which is pretty neat. And that is one of the big things with OpenBMC is really staying on the latest Yocto distribution, staying on the latest kernel, making sure we're pulling in all those security fixes as they're coming. So, master upstream OpenBMC is really right on that tip of a lot of different pieces. So we're going to talk really at the end there, the REST IPMI and the GUI, and soon to be Redfish for communication. And yeah, I think that's basically BMCs. And I talked a little bit about OpenBMC there, which is the next slide here. So what is the OpenBMC project? It's really an open source. There's kind of a long history. Facebook initially had Facebook/OpenBMC. IBM came along and said, this is cool. We're going to kind of do our own version of OpenBMC. Last year, we all got together officially and said, all right, we're going to have one OpenBMC. And a TSC was formed. So there's a group now. Let's screw this up. Intel, Facebook, IBM, Google, and Microsoft. Yes, those are the 5 founding members of OpenBMC. So a lot of tech heavyweights out there behind this, and yeah, it's been really neat seeing the community contributions going on out there. I was just talking to Sai about Facebook's got a lot of stuff coming in, Google, Intel, IBM. There's been a lot of neat stuff going into the OpenBMC community. So it really is an industry collaboration. And the whole goal was, once we all started talking, you found that everybody had their own internal BMC distribution that they've been, spending tons and tons of person years supporting and working on. And it's, it was kind of silly at times when you think about how much redundancy was going on there. And then also last year, or maybe this year, I don't know, OpenBMC did become a part of the Linux Foundation. So OpenBMC is 100% compatible with OpenPOWER, Hostboot, Opal, all of our favorite pieces out there, aka the BIOS. It's also quite compatible with the Intel chipset and UEFI as well. It can be a reference implementation. It runs on a bunch of systems. Really from a commercial perspective, the Witherspoon or the AC9222 has been the biggest system that shipped. That was the systems that IBM made for the government in that Coral contract. Supercomputer, fastest one in the world, was all based on OpenBMC-based servers out there. There's also a bunch of reference boards based on our Power 9 chip. It supports, from a BMC hardware perspective, it supports the AST2400, the AST2500. Also, there's a new Nuvoton-based chip out there that it also supports. So we've got 3 different hardware vendors, 2 different hardware vendors from a BMC hardware perspective. So the core infrastructure.
May I ask a question?
Oh, yeah.
So you're saying that only IBM sells systems based on OpenBMC. Are you aware of any other development by other vendors that would bring to the market systems running OpenBMC?
Yeah, you have a pretty good list there.
This is for example.
Okay.
Yeah, there's a lot. So
There are a lot. You know, a lot of, like our, like Google, right? I mean, they build a lot of their own internal servers. So they have a lot of systems running, running OpenBMC, but they're not going to sell those. But there's been a lot of interest and things piping up. You can tell by the upstream commits coming in. So I don't know, did you have some specifics or what were you just?
It's Yadro.
Oh,
Yeah.
Yadro.
There's the Yadro box, which is OpenPOWER. There's the Raptor computer systems, like the Talos 2 systems are all OpenBMC as well. I know there's this other processor architecture that isn't Power, but that's some special land that I'm not aware of it. But
so more importantly, Facebook's fleet runs OpenBMC.
Yeah, but the question is like somebody can buy it.
Yes, because I'm facing customers, so it's always tricky for customers to buy a system that is the only one you can find on the market.
Yeah.
No, you have
Even though it's, I understand it's better technology than BIOS or
So
UEFI.
there's a reference platform that the Facebook guys have worked on.
The reference platform, the portal.
Well, yeah.
Yeah, but that's again a developer platform.
Right, yeah, it's not a customer system.
yeah, I mean commercially we know there's Power systems available with OpenBMC. Intel ones seem to be more people putting in giant data center.
Yeah.
I think, unless.
No, the machine we're talking about.
Well, commercially, you can get typically Tian, Winstron, IBM of course, Yacto, and Raptor. Those are the 5 big ones. There are a few small players also. I know there's a French company also busy developing a server, well, a rack server for it. Mostly in the scale-out versions, you'll find more than that. You'll find some manufacturers. It's not only IBM. IBM likes to talk about Facebook and Google because those are the easy one. But from our perspective, we cannot go to Google or to Facebook and say, I would like to buy a machine. So from our perspective, that's not very relevant. Because I also have my own data center. I have a few machines, all bought through IBM because that was initially the easiest way. Today I'm talking with Tian, with Winstron, with other manufacturers because there's more than enough choice today compared to a few years ago.
Okay, so core infrastructure, we talked about Yocto, Linux. There's a lot of customization capabilities. That's actually part of the hackathon stuff later, is how do you customize OpenBMC for the system that you're building. So there's a lot of different YAML, XML. There's a lot of runtime stuff that's done via JSON. So the whole idea is that you can take that base, you can customize it for your system fairly easily, and then you've got OpenBMC running on your new system or router or whatever you got there. As we start to dig more and more into the technical details, within OpenBMC, it uses systemd, which is an open source management layer for how you run your services. It replaced, I guess, RC or init, or what, I don't know what we called that back in the day. There's been a little bit of drama behind it in the open source world, but that's what's used. From an IPC perspective, dbus is used. I'm going to talk a little bit more in detail on these later, because they're really foundational aspects that you need to understand to really work on OpenBMC. Talked about the external interfaces, journaling, tracing, debug. A lot of that is provided via systemd. Obviously, there's code update, and there's been a lot of focus. So within OpenBMC, there's a variety of work groups that we've got going. There's a big community one that happens every Monday. Everybody's invited. There's a test work group. There's a release work group where we started talking about, what is OpenBMC going to deliver from a scheduling perspective every year. And then there's also a security work group. We start to talk about vulnerabilities that are out there, different ways to harden the stack within OpenBMC from a security perspective. So lots of things out there for people that are interested. This is just talking more about some of the customization capabilities. Yocto is inherently based on this idea of pulling in recipes. So you can pick the different types of recipes and function. Do you want Python? Do you want C++? Libraries, you can pick all of these things, and it's got really neat dependency capabilities where it'll pull in, you say I want this, it'll pull in what you need. And the whole idea of Yocto was really the flexibility so that OpenBMC really can run on as many systems as possible. the IPMI capability and customizations, defining your environmental limits. Joel was just talking about his fan control algorithm on his Romulus, which is when things get too hot, you cat a file and it speeds the fans up. When they get too loud, you cat another file and it brings your fan speeds down. There's some more advanced fan control algorithms. Yeah, that's probably not really what you want to run, but you can do it, whatever you want within OpenBMC. And then, a lot of it was human readable type based stuff, so that you don't have all these crazy binary files and other pieces for customizing and getting your system running. So from a community success perspective, I think it's been really neat. Initially it was really just IBM, and you've seen people grow on, and there was a lot of people that were, a part of it, but there wasn't a lot of contributions from outside areas. But really recently, within the last year, we've really seen a big spike in contributions from a variety of sources coming into OpenBMC. So a big part of the community success has been, how many solutions are we getting? Or, are we really getting features from a lot of different areas, which we really have started to see. The different, do we have different system management things out there that can manage an OpenBMC? I think, the key for OpenBMC was to support these standard APIs like IPMI and Redfish. That's how you get support for some of these external things, which is definitely a focus of the community. There's a lot of different systems. It's tough because a lot of companies don't talk about the systems they have, so you only see these piecemeal pieces. But there's definitely a lot of things out there running OpenBMC. We had some router companies calling in for a while. They were obviously looking at OpenBMC, and that's really, we talk about it from a server perspective, but OpenBMC is really designed to manage really any type of embedded area or device or system. And then we've got a really good DevOps environment. We'll walk through that a little bit later of the end-to-end flow of when you add code and the process that it goes through. QEMU, we're gonna do some demos with that today. That's an open source simulation tool. I don't know if that's the right word for it, but it allows you to run OpenBMC images and do a lot of things. Obviously it's not your full server that you can boot, but it's really useful for a lot of the development that we do from an OpenBMC application space perspective. And then the last part of this chart is just a lot of the different links. So we've got a GitHub project. We've got a Jenkins server running out on OpenPOWER.xyz that handles the majority of our pipelines for this stuff. Code is through Garrett. So really GitHub's kind of the back end. So for the most part, from an application space development perspective, your code goes through Garrett. It goes the appropriate reviews. We've got, OpenBMC's got probably 50 or so different repositories that are all, different pieces of OpenBMC function. And we've got a good collection of maintainers, so it's not just one maintainer. There's, probably 15 to 20 different maintainers out there for the different projects. So it goes through, wherever you're putting that code, it goes through that process, and then once it's merged, it goes out to GitHub as the master repo. We've got community call, everybody's invited. We've got a mailing list, we've got IRC, we've got the tutorials, which is what we're gonna go through today for kind of getting up to speed on some of the development processes and adding a new system. All right, so that's the highest level overview, and now we're gonna kind of keep digging in. So any questions about a BMC or OpenBMC? Alrighty, how we doing? We got tea time at 10, I think, so make sure we don't miss our tea. Okay, so this next one is going to talk about, this is a quick one, and come on. Of course not. I'm going to figure this out someday, but right now I've got my little workaround.
Do you have any questions or comments from Andrew's presented so far?
Do you want to talk a bit about Redfish? What's Red?
I know very little about Redfish. It's a standardized REST API interface for management things, management BMCs, kind of things. And so in the OpenBMC space, it's been probably our most requested feature. Intel have done a bunch of work recently, kind of integrating that and hooking it up to all the internals of OpenBMC.
So so there's some largest enterprise stuff that talked about.
Yeah, I think HP led the effort to kind of
Yeah.
standardize.
Part of the problem is that IPMI was written to be produced by microcontrollers in the 90s and has the security of an open bank vault with a sign saying welcome. So with a few packets, you can actually derive the password from IPMI. So any authentication in IPMI is pure lies, right? And Redfish is the idea of like, well, what if we designed a remote API for the modern world that you could actually secure in some way and as well as be more extensible? And IPMI has a lot of limits, like you have an 8-bit number to represent like the number of sensors in the system
Yep.
or number of CPU cores, and suddenly you put it on like a decent sized computer and it doesn't fit in 8 bits. Like, so we have to like do all sorts of crazy workarounds for power boxes, but Redfish is just REST, so you're just like, well, you just have more items in a thing.
So it's the interface that you use to interact with the BMC of the network. At least in OpenPOWER systems, we're still using IPMI for in-band, so for the host processor talking to the BMC and vice versa. But yeah, Redfish would be used for querying your fleet to work out what parts are in it and what the state of the fans are and resetting the password and all this kind of thing.
So having everyone invent their own thing.
Yeah.
And
Yeah,
so it is the
it
one
is
that
definitely needed.
Yeah. I mean, it's so, it's got faults like anything, but at least it's a standard set of things.
Consistent
Yeah.
set of faults.
Yeah.
Yep. Yeah, and it's got its own versioning, and there's a DMTF website, and yeah, there's just it is neat. And so, one of the things we're trying to do, I don't know if anybody's familiar with like SIM, that we did a lot of work back in the day to support SIM, and that never really became that next management interface. So we've been kind of like holding off, but it does really look like Redfish is going to be that next management piece. So, yeah, and the cool part is, we do have a base implementation out there. It was one of those things where, yeah, Intel did the initial work, upstreamed it. Somebody forked their stuff. Amper, another company, did a bunch more work to it, and so now we've been kind of upstreaming that back into OpenBMC and yeah, getting a lot of Redfish support out there. All right, this is a quick one. This is just talking about basically where OpenBMC is. Really, the point is it is very product ready. There's a bunch of different screenshots here showing temperature sensors, showing states of the system booted, showing I believe an error log. It is shipping on a system. It's gone through a bunch of testing. So that was really the main point here. My big exciting rockets launching and fireworks going off. But it's been a fun road, and it's pretty neat to see what's going on out there. From a system management perspective, so we've got IPMI 2.0 compliance, which was a big thing, DCMI support, which is kind of your power management aspect of IPMI. It's got the REST interface. So if you look in the upper right-hand corner, we talked about how OpenBMC uses dbus. And so one of the problems you have anytime you create a new thing like this, and you provide a very open way to create external interfaces for different software components to talk, you can run, and we've all been there, you run into a lot of problems where there's no real formal way to do it, so you end up with a million of them, they're unsupported, you run into deprecation issues. So what we did is there's actually a repository out in OpenBMC called Phosphor dbus interfaces, and anytime you want to create a new interface where two components talk over dbus, you have to fill out this YAML file, basically, and it goes through a formal review process before it gets merged in, and that's really how we define our APIs, the parameters, the errors that could get passed back and forth. So that's what that is in the top right. The bottom right is just showing our web UI that's out there and has been pretty impressive. We'll do a live demo of that in a bit. Event notification, so there's a way, we've actually got this going on in the Coral systems, those high-performance systems, where you can create a client or a server on the side that's monitoring all the different OpenBMCs and opens up a WebSocket. It can get notifications of temperature changes, thermal events, different things that are of interest as you're really trying to push the limits of your systems. And then we've got some basic SNMP trap implementations where you can sign up to know when errors are generated and such. And then we've got Redfish coming from a system management perspective. Firmware update, always important. Got to be able to add those new features and fix those bugs once in a while. There's actually 2 implementations within OpenBMC to choose from. It's been somewhat of a point of contention in the OpenBMC community, but it's fine. You can pick the one you like. But there's different, TFTP, SCP, there's REST APIs to do it. We use U-boot to boot our system up, so there's some boot protection and the capabilities to swap banks if you've got multiple flash chips. We've got signed images in there now, so you can sign your images with a private key, and the OpenBMC software will verify those images before updating them. So. And then configuration and controls, this is kind of a miscellaneous page, but there's NTP time capability. We've got VLANs. You can set up VLANs on the OpenBMC. We've got a remote host console, so you can SSH to a certain port on the OpenBMC, and you'll actually see the host booting, and then be able to interact with like PettyBoot and some of those different pieces. Got VGA mirroring, so you can plug a VGA cable in the back, Jeremy, and see the VGA output. That was a kind of
Jeremy will fix all your VGA problems.
VGA, and Joel got to do quite a bit of work there too. So yeah, you want to have your crash cart and roll it up to the system. Still don't know. I'm still a little confused on our VGA, but there was a lot of people that wanted it, so it's out there. There's zeroconf, Avahi type functionality, remote logging, so you can actually, our syslog, people familiar with that. OpenBMC runs that, so there's a way to say, hey, send all your journal logs to here. You can tell the REST server on the OpenBMC to log all of the, put and post operations. So from a security perspective, you can have it log that information, output it to an rsyslog if you want to monitor the use of your server. Event logs and error logs, power and cooling management. There's a couple different fan algorithms out there for your server to look at temperatures and adjust fan speeds. Got QEMU. And then coming real soon, there's already a bunch of this code. It's either upstreamed or in the review process right now. So virtual media, so the ability to bring up your web interface and have, like a large Ubuntu installation image and be able to use the BMC to transport that image over to whatever, PettyBoot or whatever to then install that OS.
I think the key there is that it doesn't require a Java applet.
Yep. It'll be a Java applet-based one.
Yeah, just HTML5.
Yep. LDAP's just about there, so you can set up OpenBMC. Right now it's root OpenBMC as your root login to the system. So LDAP's coming, so you can log in. You can set up an LDAP server, and obviously get a little bit more security from a login perspective. KVM over IP. So this is where you can get your keyboard, video, mouse into the host operating system through the BMC over a network connection. It's just a lot of really good progress there. I guess that's another key thing is, every time this function comes in OpenBMC, there's a big focus of upstreaming that code from a Linux kernel perspective. So Joel's very good at putting the hammer down. We don't carry a lot of patches. And then obviously once you get it upstreamed, it's something that you just get every time there's an update. You don't have to worry about the maintenance. So a lot of these features are going through that way. And then we got user and group management coming, which is the ability to create local users and set up different passwords and provide different permissions. So these are the things really that the community is working a lot on right now. And that was it for that set. Any questions kind of on the high-level overview and function pieces there? All right. Yes.
I saw that the firmware updates, where are they delivered to the OpenBMC? Like, do we specify like a FTP server to get updates from, and it checks the key and updates automatically?
Well, so, like IBM manufactures and sells a system that's based on OpenBMC. So we have our own process of generating those images, assigning them, and releasing them.
So I like to ask my OEM.
Yeah.
Okay.
From a community perspective, we have a Jenkins server that is constantly building the latest code.
Yeah, okay, so there is code on the OpenBMC to perform automatic updates.
No, there is no automatic update capability.
Yeah, we can sort of make it, right?
Yeah, somebody could just point and say, hey, I want the latest build that's passed all the tests, and go grab this Jenkins image and put it on there.
Yeah, sure.
But it's kind of dangerous.
Yeah, sure, but with an audit process, like just putting a file in there, and it will do it without having to turn on the machine, like it will automatically forget about it.
There is no there's no way to say automatically go to this place and do this. You still need to interact and say, hey, I want you to go pick this image up and install it on the system.
There's
Right
no
now.
reason you couldn't.
You
make
could
it like
automate
that.
it, yeah.
Yeah, yeah.
That would be a good patch, like that'd be a good contribution.
Yeah,
Say,
sure.
here's a way to do sort of automated and staged if you want the BMCs controlling it. Typically we see like for our, when we sell someone 5,000 computers, they tend to use an external management tool that will
Yeah.
direct the BMC to do the update, so it can do sort of
Yeah.
phased updates of the cluster.
Because
So I guess it depends on the use case.
often when I'm working and I know there is an update to do, I would like just to queue it
Mm.
for the next boot. So yeah, thank you.
Mm-hmm.
One question.
Yeah.
So the brick protection that PJ mentioned, what hardware support it needs? Bigger flash or like a bigger flash?
Yeah, you gotta have,
Host of the BMC.
Pardon?
Brick protection for the host or brick protection for the BMC?
I thought that one is for BMC, right?
yeah, we have brick protection on the BMC. So if one of your flash chips gets totally hosed, the AST2500, you can actually, it'll swap you over to the other chip.
So you got to have two chips.
Yeah,
Okay.
yeah, that's
Is
really
that
all we
common
do.
in all the reference platforms that you have today? B9 reference code,
Did we only enable that?
Romulus only has one.
only on this.
Yeah.
Oh.
So the P9 reference platform is called Romulus, and yeah, that only has one. So yeah,
I
with
mean,
the
is there things which you can share actually, if that part is part of that code? I mean, so
Romulus is upstream, like the board support. Yeah. Sorry, is that what you're
like
asking?
a hardware dependency. What kind of hardware we should have?
Yeah, it's not clear. It's not spelled out anywhere. I've been taking some notes. That's one thing that we should add.
But the BMC supports two flash chips.
Yes,
Just the
BMC
board
will
that
support.
made the choice to have one.
Correct, but the switch assumes some kind of hardware as a
Device
first.
switch.
Yeah, yes, yeah, exactly. So the Witherspoon feature set requires two flash chips.
Does the XT support, like what happens if you brick your U-boot update? I guess we don't really.
Well, that's what we're just talking about.
Yeah.
It will, the watchdog will buy it, and it will select the other chip select, and boot the alternate chip. So as
Only,
long as your alternate chip is loaded with a valid firmware, it'll boot.
only if you have two chips.
Yeah, that's
But yeah.
what it's saying.
And if you have one chip, what happens at that point?
If you just erase U-boot and have one chip, then you've got a brick.
Yeah, but is there a way to recover from that?
Yeah.
Sorry, how do you
Is there
recover?
a way to recover from that?
We used to call him Cyril.
Yeah.
The guys that broom and take the chip out and reprogram it.
Yep.
You can actually,
Yeah, well, from
I'll
what
try
I
and
know,
talk about it.
some other architectures, typically if you break your firmware, the processor still can do some calls. So it typically tries to do TFTP, and then you can still flash through TFTP a recovery system.
Yeah,
Enterprise U-boot to be working now.
Yeah, of course.
The 2500 doesn't have a feature like that. The 2500 does have the ability to talk a UART-based protocol before running code. It's not publicly documented. There's a UART-based protocol that you can use for mastering an HB bus. So you can, in theory, write stuff to flash using that. There's no code to do that.
Do you know that's the serial board? Often that's a header on the board rather than something on the back of the system.
So you said you shouldn't expose the serial port certainly.
That particular serial. That feature can be strapped off. So
Yeah.
hopefully production systems will strap it off.
Hopefully. Yeah.
Yeah, we've definitely had to get people in the lab pulling chips and reflashing a lot of times. Okay, anything else?
Yeah, you guys exercise to go down the lab.
Yeah, and get your badge working again, because if you don't go for a month, it doesn't work anymore, but yeah. All right, so now we're diving deeper and deeper here. So now we're really gonna start digging into, building OpenBMC and some of the debug functionalities and capabilities here. So I mentioned that OpenBMC is really based on Yocto, Open Embedded / Bitbake. They're all kind of a same type of thing in my mind, but the communities don't think they are. But anyways, the first time you build, if you go out and just git clone OpenBMC / OpenBMC, and you do a build for one of the default systems, it's gonna take a really long time initially. But the cool thing about Yocto is that it does a really good job caching functionality. And once you've done that initial build, it'll all be differential type based builds. So all the downloads, when you do an initial build, it's like 10 gigabytes worth of data that has to get downloaded, right? Your Linux distribution, your C++ libraries, everything, and it builds it all right there on your system. So don't get, don't get too worked up about that first time. Afterwards, it's great. So that's doing a full build, though. But there's another thing you can do, which is what a lot of the hackathon items we had, which was using an SDK. So another thing that you can do, and that we do on a regular basis every time we build the latest OpenBMC code, is you can also build this SDK. So that's another fairly large thing that you download to your computer, and it will have all of the libraries and cross-compilers and pieces that you need to be able to just compile an individual OpenBMC repository, so you could just get a single application that you're working on, and then you could put it on a system or a QEMU session. You can SCP that library or that binary over, and then you can run just that. And that's really the first Hello World example we're going to do. And that's a much quicker process because there's already pre-built SDKs. Obviously, we've also got pre-built images out there on our OpenPOWER.xyz, so you can just grab the latest QEMU binary, you can grab the latest OpenBMC build, you can grab the SDK, and within a 20-30 minutes, you can actually be compiling some changes that you're making and running and verifying them. So, got some links here. That's kind of the two different ways. If you really need to build a full Flash image that you need to take to a programmer and put on a system, and everybody at some point is going to have to get to that level when you're doing OpenBMC development, then it's that first big build process. But for initial development and testing, you can definitely use the SDK environment. So dbus. Talked a little bit about dbus at the beginning. That is another open source IPC implementation that we use. That is how all communication happens on the BMC between the different processes. It has a lot of neat capabilities, asynchronous communication. It's got a very quick path, a lot of event notification where you can just monitor for a property change, for something to say, hey, this temperature has exceeded this level, so your fan controller can, instead of having these hard dependencies between services, you can just have certain pieces and functions that are monitored from different applications. Phosphor dbus interfaces, that's where we formally define all of our dbus interfaces within OpenBMC to communicate. That was that repository I talked about earlier. SDBus Plus is something that was written by the OpenBMC community. So dbus itself is just a C-based API, and we all know C++ is much better, right, Stuart? So we have a C++. So SDBus Plus is a C++ wrapper to a certain extent that we put around dbus that we use within OpenBMC in the application space. Another neat aspect of it is that those dbus interfaces that are defined in Phosphor dbus interfaces, there's a tool in SDBus Plus that takes that YAML, compiles it down into C++ code that provides basically bindings. So you can interact with your dbus APIs from a kind of a C++ object perspective. So that's really the SDBus Plus functionality. And then we've got this other piece called the Phosphor Object Manager. And so it's a piece of code that helps simplify some of the dbus communication. So as applications from OpenBMC come on the bus, is what we call it, so on the dbus bus, the object manager is monitoring for them to come on, introspecting them to see what kind of interfaces do they provide, what type of properties do they provide, and then basically the object manager provides a central location for all OpenBMC applications to talk to find other services that they want to talk to. So it prevents a lot of hard coding. So application A wants to talk to application B. They would have to, without the object manager, would have to hard code certain aspects of that interface information. And so it was really created to help optimize that and to reduce to really not have that hard coding of interface information. It also provides a way to do associations between objects. So, if you've got an error log for a thermal event, you can associate that error log with the thermal sensor that's on the dbus bus that caused that error log. So it's a different way to do things like that. It's also a way, the error log could be associated with the inventory device that basically is causing the error, right? So replace this fan would be the association you get with the object manager between an error log and a physical device. Questions? Kind of getting deep now. But we'll do some demos and hacking projects later to kind of reinforce some of this stuff. So along with these come a lot of different command line tools. So there is a mapper command line tool where you can basically do what I was just talking about, where you can say, hey, I know I want this service. I want you to tell me which dbus OpenBMC application is hosting this service that I need, this interface, this property. So there's a command line tool you can use for debug and figuring that out. Dbus itself comes with this command line called bus control, which I'm not positive it's a part of dbus, but it's definitely used to interact with dbus. And so there's different commands like tree, so you can, if you know a piece of a dbus API, like its service name, you can use the bus control tree command to see all the different things it services. You can do an introspect, which will then show you all of the properties and methods supported by that dbus API. You can read the different properties you're interested in. Within OpenBMC, there's a lot of focus on property based. So if you're setting up the network of the BMC, it actually has a lot of, those just really end up just being a lot of dbus properties. What's the address? What is the DNS server? What is just, it's all these just different properties that you set. And then internally, there's a little timer that runs on the network service that says, okay, nobody said anything for 10 seconds. It'll just restart itself, apply all those properties, and hopefully you haven't screwed it up because that is your network. So you got to be a little careful on that one. There's an OpenBMC tool, OBMC util, that you can run that comes basically standard in all the OpenBMC images that provides power on my system, power off my system, what's the state of different things. So your basic utility type wrappers. And then I've got some examples at the bottom here of bus control commands for reading properties. And it can be a little intimidating at first. It definitely was for me. But once you kind of get used to the concepts, you learn how to use kind of figure the pieces out with like the tree command and the introspect command, and it all makes a lot more sense. But reading a MAC address, looking at your auto reboot policy of your server, that type of stuff. So debug, OBMC util we talked about as just a general wrapper tool. Journal control, so systemd, which I talked about before, is for starting and stopping the services, open source application infrastructure. It has a journal, so all of the OpenBMC debug data from all of the different applications and services is written into this journal. So journal control is just the open source tool to look at your journal. It's got tons of features. Show me all the data from the current boot, from the last boot. Just show me the, from this service or this application. So it's got a ton of rich features and stuff. The most basic is just say, hey, pipe it to cat and show me the full journal. System control is interacting with your systemd units and services, which I'll talk a little bit later. But just know that system control is out there and provides a similar rich suite of functions to debug an OpenBMC system and figure out the state of different pieces. And then we've actually got a tools repository. One of the things we realized within OpenBMC at one point is everybody was writing their own tools, and none of them were getting upstream because there wasn't really a place to put it. So we did at least create this OpenBMC tools repository. It's still got, I had a bunch of tools, and it basically just has my username in there and the tools I wrote. And there was another person that had some tools, so we still haven't completely converged them, but at least they're out there, and we've got at least some common pieces. But there's one to manage your software. That's what the SFW is, where you can list the software levels and update the software, looking at different types of error logs, looking at some of the sensors, all your different power management pieces.
Question.
Yeah.
The REST-based tools means like you have to log into the BMC and then run this command, or like outside?
Yeah, you do need to, basically these, hard-coded in these tools is the login process. So as long as you're...
To clarify, this is a separate
Yeah.
machine logging over HTTP. So you have to log into the REST API and then send the commands. It's not SSHing into the machine and running it.
Oh, so
You can also do that, but that's a different thing.
Yeah. These REST-based tools are all logging in over REST and then running the commands to list the firmware, look at the events. As long as you know your password and login is root/OpenBMC, these tools will do it for you. Otherwise, yeah, you would have to give the credentials, and they would log in and do the piece.
That's a big point of differentiation between the Facebook stack and the IBM. Our common stack is that the IBM design was designed to be all managed over REST, and so you would never log into BMC.
All right, then just some references. All right, questions? Okay, one more, and then it's tea time. All right, this one is going to focus on systemd. So I've talked about it a bit. I really wanted to dig a little bit into the details behind it. And of course, I'm going to have to do my little, I have no idea why I got to run this little workaround every time, so just bear with me here. Someday I'll figure this one out. All right, so systemd. Systemd is a suite of software that provides a bunch of building blocks. It's used on a lot of Linux distributions, and OpenBMC also uses it. It provides, basically a system service manager, so you can control all of the different applications. For example, when OpenBMC first comes up, the kernel's booted. What do we need to start? What are the services that need to start? Another example is, okay, I want to power my server on. What are all the different things that need to run, and what order do they need to run to power on that server? So that's our use of systemd within OpenBMC. There's journal capability that's built into systemd, so that's where all that debug data goes. It's got some user login. We actually use the network capability, so there's a systemd network daemon that runs. So you fill in this little file with all your network information, and that service handles basically making sure that the kernel gets the right updates and your network is set up correctly. And it also has a dbus. That was another thing we like about systemd, is it has its own dbus API. So when we need to talk from an OpenBMC perspective to systemd, somebody says power on the server, we can just basically use the systemd dbus API to say, hey, go run this target to power on the system. So tons of features. It's got auto mounting features for file systems that we utilize, different C groups and different bunch of different things that, although a bit complex and complicated at times, have been very useful. So some key pieces when you look at systemd and our usage within OpenBMC. There's a lot of different types of, well, let me start. There's a unit. Everything is a unit within systemd when it comes to your, what do you start, what are you running? It's the initialization instructions for each of the processes. And so everything is a unit, but there's a different types, from a C++ inheritance object. There's a bunch of different types of units. You can have a service, you can have a target, you can have a socket, you can have a device. It kind of goes on and on and on. For this, I'm really just focusing on, from a user space application perspective, the really important units are the targets and the services. So a target is kind of that, what does the BMC need to run to get to standby? What does the BMC need to run to power on? And that's what a target is, right? A service is what you put inside the target to say, okay, these are the things that you need to run and the details on how you run them. So it defines the different types of dependencies that you have among the things that need to run to power on, to power off, to reboot, all that type of stuff. So here is a normal target file. So this is the chassis power on. So this is what you need to run to power on. And I think I took this from a Witherspoon, right? Because each system can vary. Every system would have a chassis power on, or every server where you have a chassis to power on would have a power on target. But then underneath it, the services that you have to run to power on would greatly differ. We've seen this just with the different types of servers OpenBMC powers on, right? You've got an Intel-based system, an OpenPOWER-based system, and there's actually even support for a ARM64 system out there. It really varies based on the type of processor architecture you have and the inherent ways you've set up the power and how your system boots. But all of them would have this target, and then underneath the covers they would have different types of services to do it. Some it's really simple, flip this GPIO, that's how you power on the system. Others it's more complex, you need to send this instruction to the processor, you need to do this piece and that piece. So the wants relationship is basically this target says, you know, I want this other target, and then the after is saying, and I need to make sure that I run after that target. So there's an OBMC standby target. This is basically saying, you know, don't power on the chassis until the BMC has gotten to the standby target. There's the capability to interact with that mapper that we talked about. So this is saying, hey, we can't run this target either until the service that provides the power on capability, the XYZ OpenBMC state chassis service, is up and running. So this is basically saying, telling system D, you know, don't run this target. Somebody has requested to run this target, but you really can't do it until these dependencies are in place. There's a conflict, so this kind of tells you this tells you when you can when you need to stop this target. So the conflicts is saying, hey, if somebody requests a power off, that's the OBMC chassis power off, then I need to stop the power on target. The refuse manual stop is just saying only really allow this to be stopped via conflicts operations. You know, somebody shouldn't come in and say, I want to stop this target. This doesn't really make sense. Somebody should issue a power off, which will cause the power off target to start, which will then automatically stop the power on target. And then you can even have, you know, if this target fails, if we're trying to power on the system and, you know, we can't start the fan controller, what do we want to do? And so in this case, we're saying, well, we better power off, right? Because we don't really know what the state of things are. You know, do we have power on, but we don't have fans running? Was there some sort of other problem? Well, let's be safe. If there's an issue with any of the services that this target starts, power off the system. This target, questions?
Why is there this probably background here that's complex, but why is there a power off target rather than having just a power target, which is soft and sudden?
Yeah,
Looks like.
yeah, so to have two different targets that, well, I mean, you want to, you start a target, which then starts a bunch of services. So if you stop a target, right, there's really, unless you come up with some sort of conflicts trick, right,
So
it doesn't.
It's like the exec stop for a service
That's right.
that you
Yeah.
execute when that service is.
Yeah, we've got, I mean, there's not a real good one-to-one correlation of what you
Yeah.
do to power on a system versus power off a system. So there's a lot more customization you can do with having kind of your own start and your own stop. I think there's a few examples where we were able to do that, where we could just have a single target, like FSI, I think we were able to do, or the enabling and disabling of FSI was a single. But yeah, I think in the end it was a flexibility thing.
So can the target be a collection? Like say there are multiple systems to power off and power on. Does one target solution or you have to create multiple?
Well, I mean, this is talking to a single OpenBMC, so an OpenBMC has a single target. Now,
No, OpenBMC can have multiple targets in some cases, like say you have multi-node chassis. So
Well,
you
this
can
is-
power off individually.
Well, even this is a parameterized service, parameterized target.
yeah, that's a good point. I didn't talk about that, but this is see the @ symbol means it's a templated target or parameterized one. So, you know, you can pass in like 0, 1, 2, and 3, and that would cause, it passes it on, right? So you would power on 3 chassis with that.
The target applies for the instance.
Oh, the I percentage.
Yeah, you see underneath the covers, it's calling like, percent I.
The whole like
services.
chassis with multiple stuff there, sort of been there from the start. Like we've not, as in the IBM stuff, has not shipped a system like that, and I'm not aware of anyone. Oh, you doing
Yeah,
this?
we have.
Yeah, well, I guess maybe we have somebody.
No, cool. That probably works.
We've designed in the concept. We haven't quite tested it that well, so. And I think we've agreed that 0 is always going to mean everything, right?
Yeah.
We're not going to.
Yeah, because I was looking through the API and I was doing a bunch of testing stuff there, and it's like, okay, well, how is this going to work? Like when you want to say, like, no, just power off everything. Like, you know, like I'm about to flash new firmware for testing it, like I want to return everything to a very known state and flash it. And so it was like, well, we can do this without breaking API and saying 0 is a magic number and means everything. Well, it's going to break it. But yeah,
Nope.
I think so. Yeah, that would be good to like fine tune as like that system a little bit more and actually get API stuff that's like consistent.
Yeah, we definitely have a vision that we need to support that someday, right? You get your bigger configs and systems. Okay. So this is an example. So if you go on, I think this was a Witherspoon. If you go on a Witherspoon and you look at, what does this target require? And underneath this target, there's all of these different services. So this is what it takes to power on a Witherspoon system. And you can see it's definitely not just flipping a GPIO, right? there's a lot of different services. I'm not going to go through all of them. It's just it's a neat thing about systemd is within your file system, you can just go to this directory and really see like what are the different pieces. And then if you look at all these different services, you'll see that they have ordering dependencies. So systemd will start all of these at once, and then their dependencies say, hey, you got to run this one first and this run. These ones can run in parallel. It's kind of the neat aspect of systemd. So this is a service file. This is our FSI scan service. So, not sure, yeah, so you've got the same thing in here where you've got the once, the after, you've also got a before. So different ways to say, hey, the FSI service needs to run after we've powered on the system. So that's really what's happening here. But you need to do this before you start the host. So you need to go out and get the FSI interface scanned to the OpenPOWER chip after KEK power has been applied, but before you've actually started host boot and petty boot. And then this is kind of details like, what is this service really running? And this is where you really give it the command line interface that it's running. We use this user bin env, so we don't want to hard code the path in the file system. So instead, when you use this env command line, it's saying, hey, just look at your environment, look at your path variable from a Linux perspective. It allows you to put on patches, right? So there's a certain directory that's usually not populated, but you could put your binary in there, and so the service will look there first and use it. But it's saying, hey, figure out where OpenPOWER proc control is, and call it and pass it the scan FSI parameter. So that's the, when you really dig down into the details of a service, right? That's where you're saying these are the different things you're running and how it's going to work. The syslog identifier is just saying, hey, how do you want this to show up in the journal? And other types of information, and you just say, well, call it the OpenPOWER proc control. One shot, so there's lots of different ways to configure services. This is just saying, you run this once, and then basically you're going to stop this service automatically. And the remain after exit is just a way to say if somebody happens to run this twice, we don't really want to, don't let them do that. If somebody accidentally runs it when the system's up and running. So systemd and services and target files are to a certain extent an education session in themselves, but I'm just trying to give you guys a high-level view of how we use it within OpenBMC and what the really key pieces are here.
There's some good man pages for these in the systemd.service, systemd.unit,
Yeah.
systemd.target.
Yeah, those have been the Bible for me in a lot of ways, is just really trying to understand these different features and functions. I'm not going to go too much into this one. This is just showing using system control to get the status of different targets and services on your system. So very useful debug type functionality. It'll actually show you output from the journal for the service you're giving and whether it started and ran. So just different pieces there. And then from an advanced topic perspective, the on-error, there's synchronization targets. So those are targets that don't actually have any services that they run, but you just use them to synchronize services from other targets. Something that we use for like the power on process. When you power on the chassis, there's 2 or 3 synchronization targets that we use. The templated piece, we talked about that, how your targets and your services can be templated to say, hey, power on this chassis or this chassis or this chassis, or maybe you've got multiple hosts you can start on your server, power on this host or start this host. Socket-based activation. So, like our REST server in OpenBMC doesn't start by default. It only starts when somebody actually comes in and tries to talk on the REST port. So there'll be a little delay on that first piece of communication because systemd is actually starting it based on that port activation. So kind of a neat feature to only start services on demand. And that's used in a variety of different ways. Yep, and HWMon, which is a subsystem in the kernel for providing sensor information, thermal, power, that type of stuff. Same type of thing when those pop up. In the kernel file system, we will automatically start services that start monitoring and reporting those as dbus objects. And then it's got good dbus API within systemd. That was pretty much all I wanted to talk about when it came to systemd services. Questions? I know I'm dumping a lot of information on here at the beginning, but these are all the basics of OpenBMC development that I wanted to try to get to everybody, at least get you high level knowing what these different things are and pieces are. Yeah.
So in case of the power on, like chassis power on,
Mm-hmm.
you mentioned like there's a command, right, that we run.
Yep.
User being DMV and then the command process.
Yep.
It doesn't use any debug service to kind of do it.
Well, I was just showing a little small piece. So if you really wanted to power on a system, you would there's a wrapper called OBMC util. So there's a utility tool, and you can say, hey, I want to power on the system. And that calls, within OpenBMC, there's a Phosphor state manager. So there's an application running that provides a dbus API that you can call, that tool, that OBMC util will call over dbus and say, I want to power on the system. And then that application actually then calls systemd and says, go start the power on target. And at that point, systemd takes over, starts that target, and then starts all those services that are underneath that target. So that's kind of your power on process. And whether it be the OBMC util or you call the REST API, right? So, you know, if you're in the GUI, that's using the REST API to call that Phosphor state service saying, hey, I want you to power on. And then it'll still just call systemd, and systemd really manages all the dependencies and functions there.
The same for the IPMI thing, right? So it'll do the same.
Yep.
What we do it. So it doesn't, it's decoupled the sort of interface for actually doing the things and the implementation of it. So you can easily like plug in another protocol if you want to implement, I don't know, crazy own protocol, I don't know, whatever you want. It just plugs in the same interface, and if someone goes and modifies OpenBMC to completely change how we do power on, you don't have to touch IPMI, you don't have to touch the REST API server. It's just
In case of IPMI, if you get a command to the IPMI, it just goes to the same.
Yep. Yeah, we have an IPMI daemon that's running on the server, and it calls that state service over dbus, which then says systemd start the target. So yeah.
which also means you have process isolation and stuff as well. So you have some type of living through security and resilience to bugs.
How about the failures rollback? Let's say something fails and
I mean, it's a very, you do a REST API to say, hey, go do this thing, right? Well, the state manager will then call systemd and monitor for it to complete and finish. And if it doesn't, an error log will get generated. But since it's a REST-based API, there's no real...
It could be minutes after.
Yeah, it could be minutes. Yeah. So what you have to do, what the GUI does, the user interface there, is it'll monitor for error logs to pop up and monitor for the state to change, right? Did the chassis power on? Did the host start? Because you can gather that. And if it doesn't see it over a certain amount of time, it'll report, it'll look for errors to understand what happened. So.
but in the meantime there could be some other error logs, right? So you have to look for exactly the operation you did and then what is the corresponding error log.
Yeah, you got to do a little detective work, definitely, if your system fails.
But
When
it's
you're-
not like a request response kind of thing where you do end to end.
Yeah, because it can take minutes to power on or boot your system.
Well, you spoke about a WebSocket. Would it be possible to have a monitor on the WebSocket, and when you do the REST API, get the callback on the WebSocket?
It'd be possible. You could, yeah, it's not there right now. You would definitely, could do some polling, right? And just say, hey, what's my event log? Hey, there's different things that happen. Your chassis should turn on, the physical power should turn on. And then as the host boots, there's another sensor that, the BIOS is booting, petty boot's just starting, the OS has started. So you can monitor for those types of things. And you can be looking for error logs. I'm not sure if the web UI, how much of the web UI does that, when you're interacting. But from a user, you could do it. Any other questions about the basics here? Otherwise, we can all take tea break.